So it's a pleasure to introduce the next speaker, Dr. Dayi Lin, who's a principal researcher at the Center for Software Excellence at Huawei Canada. He leads the research on trustworthy AI engineering, and his research interests include empirical software engineering, gaming, AI for software engineering, and software engineering for AI systems. So, Dayi, welcome.
Thanks for the introduction. Hello, everyone. My name is Dayi, and I'm from Huawei Canada at Center for Software Excellence. So today I'm going to talk about our thoughts on what would the foundation model in a software system actually impact software engineering of such system. We're going to start by talking about the software evolution. So Ahmed has previously mentioned briefly about this general evolution of different software systems from the most traditional codeware to where we introduce the traditional or conventional AI models, and then to promptware, agentware, and mindware. But I'd like to talk a little bit more about what does it mean for engineering. Because with each of these generation of software, what we are seeing is that it's not only just a new form of the software, it also impacts the lifecycle, the core assets, and the roles that are involved in developing such kind of software. So in another way, it's changing how the engineering paradigm that we're using to develop such software. For example, when we are moving from codeware to neuralware, what we are seeing is that there are new roles like machine learning engineers and algorithm engineers that emerged. Also, new asset types such as datasets and models become more important in this generation of software. So what happens when we're moving from traditional or conventional deep learning models to a foundation model-powered software, for example, the promptware or the agentware? We are seeing the same thing. We are also seeing new types of assets, for example, prompts, alignment data sets, agent, etc., that are changing what needs to be developed in the lifecycle, as well as how do we develop those assets with the new roles like prompt engineers, alignment engineers, etc. So this is a relatively opinionated view of how we think the development lifecycle has become in this era of foundation model applications, including promptware and agentware. So just as usual, it still starts with requirement engineering, but in this case, we have new challenges there that we might not go too much into right now. But essentially, because of the uncertainty of the behavior of foundation models, it becomes really hard to specify what's the expected behavior of the system. And then we'll move into a phase called cognitive architecture planning, which we think are very crucial but very novel in the FMware development lifecycle. What we think it's doing is that because of, in traditional software, after requirement, we would make the architecture design of the system, essentially determining how it should be implemented. What is the equivalent of traditional software architecture in FMware? We believe it's called cognitive architecture. It includes how the foundation model is interacting with other systems, how it itself is making decisions or using tools. For example, if we think about using foundation model as the reasoning engine in the application, we've seen a lot of emerging patterns such as chain of thought, tree of thought, reason acting, plan react, etc., that tries to make the decision. And all these kind of multi-round inferences and interaction with environment forms the cognitive architecture of the system. So once we design the cognitive architecture, we can start developing the foundation model application. In this phase, we first need to decide how does this foundation model application interact with its users. Because as Ahmed previously mentioned, we envision that this application is going to have a lot of interaction with human. And how does it interact with human through chat interface, through other wrappers of the traditional software needs to be decided right now. And then we need to select a model, and most often we also need to align the model to differentiate this application from a general application. And then once the model is engineered or selected or aligned, we can move on to implement such system through prompt design, which includes prompt engineering, knowledge engineering, and context engineering. And then we would decide how does this system behave. If we're thinking about a more static flow, which is most of the promptware's pattern, then we move on to the workflow engineering perspective. But if we are doing an agentware application, that's where we need to do agentification that tries to turn the software into a planning software. Of course, afterwards, we need to orchestrate all these foundation model components with the traditional components and do the thorough testing before we move on to serving operations. And throughout this new life cycle, we need to do quality assurance and trustworthiness guarantee in every step. So how does this new life cycle impact our engineering challenge? Well, we need to also think about what are the limitations of foundation models. As I briefly mentioned before, foundation models intrinsically has a lot of limitations, such as it's not really good at doing complex task planning without explicit cognitive architecture. It hallucinates by default and needs to be grounded. And also, if we do not give it an architecture that allows it to interact with the tools and environment, it has a closed-loop limitation. Combining with the new assets, new roles, and new life cycle, in engineering, what we're seeing is that there are three big groups of pain points. The first one is the low productivity for developers to develop a foundation model application. The second is the high risks of such application in the operation environment. And thirdly, is the high operational cost to run such application in a production environment. I'm going to quickly go through 10 challenges we summarized. There are a lot more details and depth for each of the challenge, and we have a preprint at the end with a QR code, and we welcome everyone to look at that and give us any feedback that you have. So the first challenge is about managing alignment data. I'm also going to show the phase of the life cycle as well as the aspects of the challenge on top of the slide for reference. So why is managing alignment data challenging, and how is it different from neural-aware? The issue is that to align a foundation model, we are facing a lot of new types of alignment data, including instructions, reference responses curated by human in natural language, all the ratings and rankings provided by human, all of which lacks engineering practices of how to curate efficiently and how to manage efficiently. And then another issue is that we're seeing a lot of foundation model, when being aligned, faces data leakage issues, where the benchmark for evaluating it were actually used in the training or alignment process, causing it to have a fake high precision or high performance, but in production, it doesn't really perform well. We're seeing a lot of benchmarks and leaderboard that shows models that has really good performance, but it really doesn't work well in production. And then finally, another issue that we're seeing is that to accurately and quantitatively decide how much data is needed and how much human effort should be put into aligning the model is also very hard to define. So what is the state of practice for people to solve this problem? We're seeing that people are using active learning or weak or self-supervision to try to solve it. Some examples include Snorkel, which is a which is a data alignment company that uses data programming to solve such problem. But the issue is that because of the new data programming paradigm, it's actually pretty hard to debug the whole alignment process. And then we're also seeing new methods like self-instruct that tries to generate the alignment data automatically. But we are also seeing the issue of model collapse, where when there's no new information provided by human, the model would actually start forgetting its pre-training behavior. So what do we think we should do moving forward? We believe that we need to invest in researching what are the low manual intervention auto-labeling methods could be developed, and also try to utilize open and inner source mechanism to curate the data and its license compliance guarantee. The next challenge we are seeing is about crafting effective prompts. So what are the problems of developing prompts? We say that there's a field called prompt engineering right now, but essentially it's still hacking because prompts are too low level and too fragile right now. It's directly dealing with what are the input to the model at the lowest level, at the token level. So it's also very sensitive to tiny changes. A lot of times, just by phrasing a question slightly different or even changing one token slightly, you greatly impact the outcome, causing people constantly trying to do trial and error to find the best way to prompt. Another issue is that prompts are not transferable, meaning that if the model evolves, then we have to keep updating the prompt, keep re-debugging the prompt so that it can keep up with the evolution of model. It also happens when we need to replace a model. If we no longer wish to use one type of model and we want to switch to a different one, we need to re-optimize all the prompts as well. And finally, current prompting lacks transparency and reproducible results. A lot of times, even when we try to control all the parameters, all the environment, for the same prompt, we're still seeing different results after different runs, making it really hard to debug. So currently, the state of practice is that firstly, a lot of efforts are put into ensuring the inference transparency of prompt, where the tools will show you the sampling probability and token level attribution of the prompt. But it lacks the high-level abstraction for developers to debug how to optimize the prompt. And another method people are using is automated prompt optimization through reinforcement learning or other search-based methods. But most of these methods are focusing on token level in isolation from other aspects that will impact the outcome of the prompt, such as the model choice, the inference parameters, and hardware environment. So we believe that moving forward, the innovation path should be, firstly, we need to elevate what are the level we're using to prompt a foundation model application to try to express higher level intent rather than lower level token input. And also we need to make sure that the prompting method is transparent and can be debugged. And we also need to look into how can we do reproducible prompting so that we can productively debug a prompt behavior. So next challenge, the third challenge is dealing with the multi-generation software. A lot of times when we're looking at applications and demos coming out online, they're really fancy, really cool, but they kind of assume that foundation model applications are greenfield software development where we start with a new project every time. But a lot of time in enterprise setting, we have to actually improve a existing software or integrate existing software with a foundation model powered FMware. So what are the issues there? To integrate different legacy software systems, we're facing a lot of different data models and different communication protocols. How can we actually effectively wrap them and make them communicate with the foundation model component is pretty challenging. We have to put in a lot of engineering effort to do that. And also, if the shared legacy system across multiple foundation modelware changes, it impacts all the downstream foundation model applications. What are we seeing as the state of practice? We're seeing that a lot of people are doing the plugin mechanism for more static promptware where, for example, ChatGPT allows you to enable certain plugins where they provide a certain metadata for the model to decide whether to use the plugin or not. Or in agentware situations, we also sometimes wrap the legacy software as tools to be used by foundation model applications. But both of these methods requires developers to repackage existing software systems and tools to be compatible with foundation model applications. So the innovation path forward is that we firstly need to realize foundation model application is not always a greenfield project. And then we need to come up with mechanisms to reusable modular integration of legacy systems. So next big challenge is about controllability. Controllability is a very important subject here because of the intrinsic randomness of foundation model applications. But in a lot of software domains that requires high trustworthiness, we actually need robust controllability of software's behavior. For example, in healthcare, autonomous driving, or any other sensitive areas. So the state of practice are generally grouped into two categories of techniques. One is using restricted approaches, where we try to limit the autonomy of the foundation model by providing standard operation procedures, SOP, and standard work instructions, SWI, in prompts or through a state machine inside the cognitive architecture. But of course, we do want to leverage the planning and reasoning capability of foundation models. So what we're also seeing, on the other hand, is that we do let the model plan, but we provide human oversight. So for example, GitHub's latest projects usually would involve human oversight to oversee whether the foundation model planning is accurate before it's carried out. So the innovation path forward, we believe, can borrow some ideas from traditional software where we actually build models of application permission control for a lot of systems, for example, Android. Can we utilize similar method to build up the fine-grained boundaries for what is safe and what is controllable of a behavioral foundation model systems? And also, can we try to separate different levels of autonomy? For example, we let the model decide high-level planning at a higher level, and that level is controlled or overseen by human, but we allow the models or the foundation model applications do some low-level autonomy decisions in this cognitive architecture. Such separation of layers might also address the issue. And then another big challenge we are seeing right now is about compliance and regulations. And the problem here is that there are a lot of new government regulations coming out all the time, including the recently coming into effect UAI Act that requires transparency and human oversight of such systems. And also there are old regulations like GDPR requiring personal data to be protected. But the issue here is that if a lot of applications are treating foundation model as an API call that's hosted somewhere else, especially external of the organization, then using these third-party foundation model services will require data transmission outside the boundary of data protection within the organization. So how can we ensure compliance in this case is pretty challenging. And then not to mention the whole development process involving several different aspects of license compliance for data, model, and also the generated outcome. And also, even when we're using an open source model, a lot of times we're bounded by the ever-changing terms of such models that could pose compliance risks for application. So the state of practice usually involve heavy manual process, such as documentation and risk management framework. Beyond the process, we are also seeing people doing work in the data and AI license field that focus on individual foundation model application or dataset licensing. But such individual foundation model and dataset licensing disregards license interaction among different assets. And also, if we are thinking about agentware, and the agentware is ever evolving, how does this evolution nature pose risks to compliance is a brand new problem as well. The innovation path forward, we believe, are three parts. The first one is that we need tools that's capable of automatically determining the foundation model where bombs to provide traceability and transparency of such software systems. And then we also need ways of testing and formal verification of regulations in license compliance. And finally, we need to develop privacy-preserving techniques for foundation model applications in regard to data transfer outside of the organization bound. The sixth challenge we're seeing is the limited collaboration support throughout the whole life cycle. There are three big problems we're seeing here. The first is to enable collaborative development. In traditional software sense, we heavily rely on version control systems, a lot of times distributed version control systems, to enable multiple developers to work on the same software. But in foundation model applications, what to version and how to version them becomes a big challenge. Because firstly, the data types are new. They have different structures, and they have evolving nature. They might change as they function in the environment, such as agents. How and when to version them becomes a pretty challenging topic compared to traditional assets such as code. And then what formats and standards to use to version them is also challenging because right now we lack a standard to provide interoperability across different platforms, different development tools, and different organizations. So a lot of assets cannot be freely shared. And then finally, how do we package and distribute such software system also becomes pretty challenging in regards to new asset types. So state of the practice is that a lot of people just treat all the assets as text and use traditional Git to organize and version them. But this is ignoring the uniqueness of these new assets, their structured nature, and cannot facilitate efficient collaboration development or reuse. There's also no established standard or established hub for this kind of asset management and sharing. So the innovation path forward would be we need to develop granular version control mechanism to facilitate collaborative development and reuse of assets. And we also need standard and protocols for interoperability of such software systems. The seventh challenges, we are now looking at operation and semantic observability issues. There are two areas here. The first one is to enhance the existing observability infrastructure for traditional software. we're looking at new metrics such as token consumption, groundedness, environmental interaction of the legacy system. But we also need new type of telemetry systems to monitor explicit and implicit user feedback so that we can improve the system. The state of practice is that we need to, there are several closed source platforms that provide such observability, but they are not providing dynamic multi-agent support yet. And also semantic signal is used in certain applications, but there's no general solutions available. So the innovation path forward is that we need to observe diverse aspects of the enhanced metrics of this complex system, but we also need advanced generalizable semantic signal telemetry systems. We have 3 more challenges left. I'm going to try to be a bit fast here for time's sake. The first one is about performance engineering. We know that performance engineering is even bigger problem in foundation model application because foundation model inference is very costly and slow, especially when the model inference happens several rounds in application for the complex cognitive architecture. When we are only ensuring the model level SLA, we cannot guarantee the application level SLA because there are multi-rounds of inferences. So if we are self-hosting such application, we also face the issue of if there are multiple models but limited hardware, we need to constantly switching the loaded models, which is a performance bottleneck. There are several practices being done right now to try to optimize for performance, including model compression, prompt compression, and semantic caching. But they don't really solve the issue of performance bottleneck at the application level. So moving forward, we believe that we need to focus on a foundation model application level as a guarantee by utilizing the intent preserved in a declarative abstraction of applications. Another big problem we are seeing right now is to test the foundation model application under the non-deterministic nature of it. Because generative tasks doesn't have a ground truth, and every test is flaky when the reproducibility is not guaranteed. That means that it's very hard to specify the test oracles and specify test cases of the foundation model applications. And because of the operational cost, to run a test set also becomes really expensive. There are 2 ways of doing this right now. One is that we use human in the evaluation process, but it's very costly and very slow. Another way is we use the foundation model itself as an evaluator, for example, GPT-4, to evaluate the application. This is a very common practice right now, but our worry is that sometimes it's not really well aligned with human. We are seeing that in certain tasks, it only has like a 50% agreement with human evaluation. So the path forward is to define and evaluate quality of foundation model application with low human efforts and high reliability. The last challenge we are seeing right now is about all of these different lifecycle supports needs different tools. But right now, a lot of tooling efforts are siloed, and there's a lack of comprehensive process for this whole lifecycle. This will cause a lot of context switching and cognitive overload for developers to slow down development. So the state of practice, there are a lot of ongoing efforts from different organizations to try to develop tools, but they often cannot cover the whole lifecycle or miss critical areas such as compliance, or it cannot be extended. So the innovation path forward is that we need a unified platform to provide cradle-to-grave lifecycle support and extensibility. We're trying to tackle these challenges in an effort that we are not going to go in detail for. We believe it has to be divided into 3 layers in hubs, frameworks, and runtime to solve all these problems. And all these problems are detailed in a preprint, as we mentioned before, that you're free to look at and understand better what our thoughts on these challenges are. But at the end, the take-home that we do want to leave people is that these challenges cannot be solved by individual organizations or researchers because a lot of them needs community effort, like establishing standards, establishing license, having interoperability across different toolings. They all need the community efforts. So we believe this is a very new and exciting area, and we look forward to collaborate with you all to advance this area. Thank you.
Thank you very much, Dayi.